When installing electric heat FCU, understanding the National Electrical Code, or NEC, requirements for branch circuit wiring, overcurrent protection, and disconnect sizing is crucial. According to NEC Section 424.3b, the branch circuit wiring and overcurrent protection device for electric heat FCU must be sized at 125% of the load. Let's say the actual load is 55 amps. To determine the minimum ampacity for the branch circuit wiring and the overcurrent protection, you multiply the actual load by 125%. In this case, 1.25 times 55 amps equals 68.75 amps. Therefore, the branch circuit wiring and breaker must be rated for at least 68.75 amps. Now let's discuss the pull-out disconnect switch. A pull-out disconnect provides a means of disconnecting the circuit, which is useful for maintenance, repairs, and in case of emergency. The question is whether a 60 amp pull-out disconnect is acceptable for a 55 amp load in an electric heat FCU application, or if a higher rated disconnect is required. The answer is yes, a 60 amp pull-out disconnect switch is generally acceptable in this scenario. Pull-out disconnects are not typically required to be rated at 125% of the load. While the branch circuit wiring and overcurrent protection must be sized at 125%, this requirement does not usually extend to the pull-out disconnect itself. The NEC considers the load on electric heat FCU to be continuous, which means the load is expected to operate for 3 hours or more at a time. Because of this continuous nature, the branch circuit wiring and overcurrent protection must be sized at 125% to account for the sustained load. However, the pull-out disconnect is primarily a safety device intended to energize the circuit when needed. It is not continuously carrying the full load current. Therefore, it is not subject to the same 125% sizing requirement as the branch circuit wiring and overcurrent protection. This means that a 60 amp pull-out disconnect is rated to handle 60 amps of continuous current. As long as the actual load does not exceed the disconnect's rating, it will function safely and effectively. In summary, you can install a 60 amp pull-out disconnect switch for your electric heat FCU without violating code requirements, provided the actual load does not exceed 60 amps. While the branch circuit wiring and overcurrent protection must be sized at 125% of the load, this requirement does not apply to the pull-out disconnect itself. The pull-out disconnect is considered a continuous duty switch but is not subject to the same 125% upsize. Now let's delve further into the considerations of the National Electrical Code, or NEC, and related electrical principles so you have a more comprehensive understanding of these requirements. The NEC serves as the cornerstone for safe electrical installations and practices. It's a comprehensive document that outlines the minimum standards for electrical wiring, equipment, and systems. Compliance with the NEC is not just a matter of best practice, it's often a legal requirement enforced by local and national authorities. Understanding the NEC structure and how to navigate it is essential for any electrician or electrical engineer. The NEC is organized into chapters, articles, and sections, each addressing specific aspects of electrical installations. For example, Chapter 4 pertains to equipment for general use, while Chapter 2 covers wiring and protection. Article 424, which includes Section 424.3b, deals specifically with fixed electric space heating equipment. To effectively use the NEC, it's important to familiarize yourself with its layout and terminology. The code uses specific definitions and terms to ensure clarity and consistency. For instance, the term continuous load has a precise meaning in the NEC, which affects how conductors and overcurrent devices are sized. When working on electrical installations, it's advisable to have a copy of the latest NEC readily available for reference. Many resources offer online access to the NEC, but a physical copy can be easier to navigate and annotate. Additionally, consider attending NEC training courses and workshops to deepen your understanding of the code and its applications. Let's delve deeper into the concept of continuous loads and their impact on electrical installations. Understanding continuous loads is critical because they affect the sizing of conductors, overcurrent protection devices, and other components in an electrical circuit. The NEC defines a continuous load as a load where the maximum current is expected to continue for 3 IOs or more. This sustained current flow generates heat in conductors and equipment, which can lead to insulation degradation, equipment malfunction, and even fire hazards if not properly addressed. To account for the effects of continuous loads, the NEC requires that conductors and overcurrent protection devices be sized at 125% of the continuous load current. This upsize provides a safety margin to prevent overheating and ensure reliable operation. For example, if a circuit is expected to carry a continuous load of 40 amps, the conductors must be sized to handle at least 50 amps, 40 amps, 1.25 equals 50 amps. Similarly, the overcurrent protection device, such as a circuit breaker or fuse, must also be rated for at least 50 amps. It's important to note that the 125% rule applies only to the continuous portion of the load. If a circuit serves both continuous and non-continuous loads, the continuous load is multiplied by 125%, and then the non-continuous load is added to the result to determine the total ampacity requirement. To determine whether a load is considered continuous, consider the operating characteristics of the equipment and the expected duration of use. For example, lighting in a retail store or a large office building is typically considered a continuous load because it operates for extended periods. Similarly, heating and cooling systems, such as electric heat FCU, are often classified as continuous loads, especially in climates where they operate for many hours each day. In contrast, appliances like dishwashers or washing machines are usually considered non-continuous loads because they operate for relatively short durations. Now, let's consider the characteristics and the application of pullout disconnect switches. A pullout disconnect switch is a type of manual disconnect device used to de-energize an electrical circuit or piece of equipment. It typically consists of a switch mechanism enclosed in a metal or plastic housing, with a handle or lever that can be manually operated to open or close the circuit. Pullout disconnect switches are commonly used in HVAC systems, motor control circuits, and other applications where local means of disconnecting power is required for safety or maintenance purposes. They provide a visible and reliable way to ensure that a circuit is de-energized before work is performed on the equipment. There are several types of pullout disconnect switches available, each designed for specific applications and voltage ratings. Some are rated for general purpose use, while others are designed for heavy-duty or industrial applications. The choice of pullout disconnect switch depends on the voltage, current, and environmental conditions of the installation. One of the key advantages of pullout disconnect switches is their simplicity and ease of use. They are straightforward to install and operate, and they provide a clear visual indication of whether the circuit is open or closed. Additionally, pullout disconnect switches are generally robust and reliable, requiring minimal maintenance over their service life. When selecting a pullout disconnect switch, it's important to consider the following factors. The voltage and current rating must be appropriate for the circuit being disconnected. The switch must be rated to interrupt the maximum fault current that could occur in the circuit. The enclosure must be suitable for the environmental conditions of the installation, such as temperature, humidity, and exposure to corrosive substances. The switch must comply with applicable standards and regulations such as Underwriters Laboratories UL or Canadian Standards Association CSA listings. Now, let's discuss the overcurrent protection devices like circuit breakers and fuses. Overcurrent protection devices are essential components in an electrical system designed to protect conductors and equipment from damage due to excessive current flow. Circuit breakers and fuses are the two primary types of overcurrent protection devices. Both devices interrupt the flow of current when it exceeds a predetermined level, preventing overheating, insulation damage, and potential fire hazards. A circuit breaker is a resettable overcurrent protection device that automatically interrupts the circuit when an overcurrent condition occurs. It consists of a mechanical mechanism that trips open when the current exceeds its rated value. Once the overcurrent condition is cleared, the circuit breaker can be manually reset to restore power to the circuit. Circuit breakers are available in various types and sizes, including thermal magnetic, electronic, and instantaneous strip breakers. Thermal magnetic circuit breakers use a combination of thermal and magnetic elements to detect and respond to overcurrent conditions. Electronic circuit breakers use electronic circuitry to monitor current flow and trip the breaker when necessary. Instantaneous trip breakers are designed to quickly interrupt very high fault currents. A fuse is a non-resettable overcurrent protection device that contains a fusible link that melts and opens the circuit when an overcurrent condition occurs. Fuses are typically less expensive than circuit breakers but must be replaced after they have blown. Fuses are available in various types and sizes, including cartridge fuses, plug fuses, and blade fuses. Cartridge fuses are commonly used in industrial and commercial applications, while plug fuses are typically used in residential applications. Blade fuses are used in automotive and electronic equipment. When selecting an overcurrent protection device, it's important to consider the following factors. The current rating must be appropriate for the circuit being protected. The interrupting rating must be high enough to safely interrupt the maximum fault current that could occur in the circuit. The time current characteristic must be suitable for the application. The device must comply with applicable standards and regulations such as UL or CSA listings. The time current characteristic of an overcurrent protection device describes how quickly it will trip or blow in response to different levels of overcurrent. Some devices are designed to trip quickly in response to high fault currents, while others are designed to tolerate temporary overloads without tripping. The choice of time current characteristic depends on the specific application and the type of equipment being protected. Now let's explore the different types of wiring and conductors used in electrical installations. Electrical wiring and conductors are the pathways through which electrical current flows from the source to the load. The selection of appropriate wiring and conductors is crucial for ensuring safe and reliable operation of an electrical system. The NEC specifies the types of conductors that can be used in different applications as well as the allowable ampacity of each conductor size. Conductors are typically made of copper or aluminum, each with its own advantages and disadvantages. Copper conductors have higher conductivity and are more resistant to corrosion than aluminum conductors. However, aluminum conductors are lighter and less expensive than copper conductors, making them suitable for certain applications. The ampacity of a conductor is the maximum amount of current it can safely carry without overheating. The ampacity of a conductor depends on its size, insulation type, and installation method. The NEC provides tables that list the allowable ampacities of conductors under various conditions. When selecting conductors, it's important to consider the following factors. The ampacity must be sufficient to carry the expected load current. The voltage drop must be within acceptable limits. The installation type must be suitable for the environmental conditions of the installation. The conductor must comply with applicable standards and regulations such as UL or CSA listings. There are several types of wiring methods commonly used in electrical installations, including non-metallic sheathed cable, NM cable, metallic conduit, and cable tray. NM cable, also known as Romex, is a type of electrical cable consisting of two or more insulated conductors enclosed in a non-metallic sheath. NM cable is commonly used in residential wiring for branch circuits and lighting circuits. Metallic conduit is a rigid or flexible metal tubing used to protect electrical conductors from damage. Metallic conduit is commonly used in commercial and industrial applications, as well as in areas where the wiring is exposed to physical damage. Cable tray is a support system used to route and support electrical cables in industrial and commercial buildings. Cable tray provides a flexible and cost-effective way to manage large numbers of cables. Now, let's consider the impact of voltage drop on electrical installations. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce lighting brightness, and increase energy consumption. The NEC recommends that voltage drop be limited to a maximum of 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals current times resistance, where current is the current flowing through the conductor, and resistance is the resistance of the conductor. The resistance of a conductor depends on its length, size, and material. To minimize voltage drop, you can use larger conductors, shorter wire runs, or conductors with lower resistance. You can also use voltage drop calculators to estimate the voltage drop in a circuit. When designing an electrical system, it's important to consider voltage drop and take steps to minimize it to ensure optimal performance and efficiency. By understanding the principles of voltage drop and using appropriate wiring methods, you can ensure that electrical equipment operates safely and reliably. Now, let's delve into the concept of grounding and bonding in electrical systems. Grounding and bonding are essential safety measures designed to protect people and equipment from electrical shock and fire hazards. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to quickly interrupt the circuit. Bonding connects all metal parts of an electrical system together to create an equipotential plane, preventing voltage differences that could cause electric shock. The grounding system typically consists of a grounding electrode, such as a ground rod or metal water pipe, connected to the equipment grounding conductor EGC. The EGC is a conductor that runs with the circuit conductors and is connected to the metal enclosures of electrical equipment. In the event of a ground fault, the fault current flows through the EGC back to the source, tripping the overcurrent protection device and energizing the circuit. Bonding is achieved by connecting all metal parts of an electrical system together using bonding jumpers or bonding conductors. This includes metal conduits, metal enclosures, metal equipment frames, and metal water pipes. By bonding all metal parts together, any voltage differences that may occur are minimized, reducing the risk of electric shock. The NEC specifies the requirements for grounding and bonding in electrical systems. It outlines the types of grounding electrodes that can be used, the size of the grounding and bonding conductors, and the methods for connecting grounding and bonding conductors to equipment. When installing electrical systems, it's important to follow the NEC requirements for grounding and bonding to ensure the safety of people and equipment. Improper grounding and bonding can create dangerous electrical hazards, including electric shock and fire. By properly grounding and bonding electrical systems, you can minimize the risk of electrical hazards and ensure the safe and reliable operation of electrical equipment. Now let's discuss some common electrical safety practices to keep in mind. Electrical safety should always be a top priority when working with electrical systems. Following safe work practices can help prevent electrical shock, burns, and other injuries. Here are some common electrical safety practices to keep in mind. Always de-energize circuits before working on them. Use a voltage tester to verify that the circuit is de-energized before touching any wires or equipment. Wear appropriate personal protective equipment such as safety glasses, rubber gloves, and insulated tools. Never work on electrical equipment in wet or damp conditions. Keep work areas clean and free of clutter. Use ladders and scaffolding safely. Inspect electrical cords and equipment regularly for damage. Replace damaged cords and equipment immediately. Use ground fault circuit interrupters GFCIs in wet locations, such as bathrooms, kitchens, and outdoor areas. Follow lockout/tagout procedures when working on de-energized circuits. Never overload circuits or extension cords. Use extension cords only temporarily. Know the location of emergency shut-off switches and fire extinguishers. Be aware of potential electrical hazards in the work area. Report any electrical hazards to your supervisor. By following these electrical safety practices, you can minimize the risk of electrical accidents and ensure a safe working environment. Remember, electrical safety is everyone's responsibility. Now let's talk about the importance of electrical inspections and maintenance. Regular electrical inspections and maintenance are essential for ensuring the safe and reliable operation of electrical systems. Inspections can identify potential problems before they become serious hazards, while maintenance can keep equipment in good working condition. Electrical inspections should be performed by qualified electrical inspectors who are familiar with the NEC and local electrical codes. Inspectors will check for common electrical hazards, such as overloaded circuits, damaged wiring, and improper grounding. They will also verify that electrical equipment is installed correctly and that it meets safety standards. Electrical maintenance should be performed by qualified electricians who are trained to work on electrical systems. Maintenance tasks may include tightening connections, replacing worn parts, and testing equipment. Regular maintenance can help prevent breakdowns, extend the life of equipment, and improve energy efficiency. The frequency of electrical inspections and maintenance depends on the type of electrical system and the environment in which it operates. High-risk environments, such as industrial facilities and construction sites, may require more frequent inspections and maintenance than low-risk environments, such as residential homes. It's important to keep records of all electrical inspections and maintenance activities. These records can be used to track the condition of electrical equipment and to plan for future maintenance. By performing regular electrical inspections and maintenance, you can ensure the safety and reliability of electrical systems and prevent costly breakdowns. Regular inspections and maintenance will also help to identify any potential safety hazards that need to be addressed. Now let's talk about energy efficiency and how it relates to electrical installations. Energy efficiency is the practice of using less energy to perform the same task. Improving energy efficiency can save money, reduce pollution, and conserve natural resources. There are many ways to improve energy efficiency in electrical installations. Use energy-efficient lighting, such as LED bulbs. Install occupancy sensors to turn off lights when rooms are unoccupied. Use programmable thermostats to control heating and cooling systems. Install energy-efficient appliances and equipment. Improve insulation to reduce heat loss. Seal air leaks to prevent drafts. Use power strips to turn off electronic devices when they are not in use. Install solar panels to generate electricity. Conduct an energy audit to identify areas where energy can be saved. Educate occupants about energy conservation practices. By implementing energy-efficient measures, you can reduce your energy consumption, lower your utility bills, and help protect the environment. Energy efficiency is not only good for the environment, but it can also save you money in the long run. By making smart choices about energy use, you can reduce your carbon footprint and contribute to a more sustainable future. Energy-efficient electrical installations are not only environmentally friendly, but they can also improve the performance and reliability of electrical systems. By using high-quality, energy-efficient components, you can reduce energy losses, improve power quality, and extend the life of equipment. By taking steps to improve energy efficiency in your electrical installations, you can save money, reduce pollution, and create a more sustainable future. Energy efficiency is a win-win for everyone. Now let's discuss the importance of staying up to date with electrical codes and standards. Electrical codes and standards are constantly evolving to reflect new technologies, safety concerns, and best practices. Staying up to date with the latest codes and standards is essential for ensuring the safety and compliance of electrical installations. The NEC is updated every 3 years to incorporate changes and improvements. It's important to have access to the latest edition of the NEC and to be familiar with its provisions. In addition to the NEC, there are other electrical codes and standards that may apply to specific types of installations or equipment. These may include standards from organizations such as UL, IEE, and ANSI. To stay up to date with electrical codes and standards, you can subscribe to industry publications, attend training courses, and participate in professional organizations. You can also consult with electrical inspectors and engineers to get clarification on code requirements. Staying informed about electrical codes and standards is not only important for compliance, but it can also help you improve your knowledge and skills as an electrician or electrical engineer. By understanding the latest codes and standards, you can design and install electrical systems that are safe, efficient, and reliable. Staying up to date with electrical codes and standards is a continuous process. It requires a commitment to ongoing learning and professional development, but the benefits of staying informed are well worth the effort. Now, let's talk about the importance of proper documentation and record keeping for electrical installations. Proper documentation and record keeping are essential for managing and maintaining electrical systems effectively. Accurate records can help you troubleshoot problems, plan for maintenance, and ensure compliance with regulations. Electrical documentation may include drawings, specifications, calculations, and test reports. Drawings should show the layout of the electrical system, including the location of equipment, wiring, and controlled devices. Specifications should describe the materials and equipment used in the installation, including their ratings and performance characteristics. Calculations should demonstrate that the electrical system meets the requirements of the NEC and other applicable codes and standards. Test reports should document the results of electrical tests such as insulation resistance tests and ground impedance tests. Records should be kept for all electrical inspections, maintenance activities, and repairs. These records can be used to track the condition of electrical equipment and to plan for future maintenance. Proper documentation and record keeping can also be helpful in the event of an electrical accident or incident. Accurate records can provide valuable information for investigations and can help prevent similar accidents from happening in the future. Electrical documentation should be stored in a safe and accessible location. Electronic records should be backed up regularly to prevent data loss. Proper documentation and record keeping are essential for managing and maintaining electrical systems effectively. By keeping accurate records, you can ensure the safety, reliability, and efficiency of electrical installations. Proper documentation and record keeping also demonstrate due diligence and compliance with regulatory requirements.